Okay, so now you know what an epoxide is, and so now we're going to move on to what do they do when we react them with other things. And so this is where we start to see a lot of the similarities to carbonyls. So let's say that we have an epoxide. So I'm going to take, um, I'll just take still bean. I treat it with MCPBA. And as we learned last time, that means that we will end up with an epoxide in the middle here where this double bond is. And because I have a trans double bond, we expect this epoxide to be a trans epoxide as well. All right, so we got two benzene rings. I pretend my benzene rings are, one is forward, one is back, because we had one up and one down on the other side. Now, one of the ways that we react epoxides is we can react them with H plus and an alcohol. So I'm just going to use methanol, but of course any alcohol will work there. So going back to what we learned in our most recent units, right? We would say we see H plus, we think, okay, that's going to add to some kind of carbonyl oxygen or something like that. And that's exactly what happens. Only instead of a carbonyl oxygen, we're going to use this epoxide oxygen, add H plus to that. And what we get now is something that looks like this. Right? We end up with a positive charge on that oxygen. And so now we've gone from having a really good leaving group over here in this epoxide in this three-membered ring with all this extra strain on it. We go from having a really good leaving group to having an even better leaving group because now we've got a positive oxygen there. And so even though we have a pretty terrible nucleophile in methanol, this is still good enough that it's going to come in, it's going to attack this position, break that CO bond, and make an additional lone pair on the oxygen, right? And so all of this is very similar to what we did with the carbonyls. We've seen this before in SN2 reactions. This is, in fact, an SN2 reaction, and it's an SN2 reaction that's happening at a stereocenter. So if we think back to what we have learned about those, we know what's going to happen here. So this OH group now, right, we've broken this carbon-oxygen bond on this side, so this carbon and this oxygen are no longer connected, so we just have a OH group there, and then we've got a benzene ring going back, and there's an implied hydrogen that's going forward here that I haven't drawn in, but I will draw in now. And then what's happening at the point of reaction is probably the more interesting one, because at the point of reaction with an SN2 reaction, we always get inversion of stereochemistry. Right? And so with epoxides, it's no different. So this time, our leaving group um, is up, and so we have to come in 180 degrees from that, and so that means that our nucleophile is going to end up being a straight line bond that's kind of pointed down, right? So if we think about where the leaving group was, I'll draw in that dashed line here, right? We want our nucleophile, our methanol, to come in 180 degrees from that. So if you pretend that I was better at drawing, then that's about 180 degrees. Now what happens to our benzene ring is our benzene ring just kind of gets pushed out of the way. It just moves up here. And then the hydrogen that was also there is implied to have switched as well. Right. So use H plus to neutralize this whole thing and we get our final product. We've got an OH there, we've got an OCH3 here, we've got hydrogen, we've got benzene ring, and we've got a benzene ring over here. I don't know who chose all these benzene rings for this molecule, but I'm kind of annoyed right now. All right, and so this is our final product. And notice what's happened at this stereocenter is that we have inverted this stereocenter. If we go and assign priority numbers and assign R or S to this stereocenter in our starting material, right, the oxygen would be the highest priority number because it has the highest atomic number. We have carbons on either side. This one has fewer hydrogens, so this one will be 2. This one will be 3, and then the hydrogen that's not shown would be 4. So hydrogen that's not shown would be 4. So this will be an R. No, this would be an S stereocenter. Haha, right? This would be an S stereocenter, excuse me. In this case, we go from 1 to 2 to 3. We have our fourth group going back, so this is an S stereocenter. And then down here in the product, you'll notice that if we do the same thing, right, we have 1, 2, 3, 4. In this case, when we go from 1 to 2 to 3, we're going in a clockwise direction, and so this one is going to be R. So we've inverted the stereocenter. And we did that because we brought in our nucleophile 180 degrees from our leaving group. So every time that we do an addition or nucleophilic addition to an epoxide, we're going to go through SN2, we're going to have to do inversion. So there's going to be a few stereochemistry things that we have to worry about. Let's do an example with a cis double bond just for the fun of it. We'll just take butene. It's a nice easy one. MCPBA. We get the cis epoxide, and then we're going to treat this with some alcohol. I'm going to let's use ethanol this time, just for something different, an H+, and we're going to get the same thing, right? Epoxide goes and gets the H+, we get this activated epoxide. Now we've made ourselves a really good leaving group here. Our methyl groups are still present. It doesn't matter what I think in this case we have an R stereocenter at this position, but it doesn't matter. Now I'm going to have ethanol come in. It's going to attack this carbon. We're going to break the carbon-oxygen pi bond and make a lone pair on the oxygen. So notice that I attacked the other side this time. In this case, it doesn't matter which side we attack because the epoxide that we're using is symmetric. We have a methyl group on one side, we have a methyl group on the other side. So either one that we attack ends up being, we end up getting the same product out. So you can confirm that if you want. You can take the same epoxide that I just drew, have your ethanol attack the other oxygen, and just confirm for yourself that we end up with the same product. We always do. Well, we always do when it's symmetric at least, right? So once again, I'm going to make the OCH, oops, it's not OCH3, it's ethanol this time. That's going to be opposite the leaving group, right? So if this was our leaving group bond that we broke, then the nucleophile has to be 180 degrees from that. And we're going to have our methyl group pointed up here this time. So initially this has an H+ on it, but we can easily lose the H+. I'm going to do that with eraser chemistry because I'm lazy, and we'll get this as our final product. So that takes care of the stereochemistry there. Now, I think the main thing that's probably, the main question that's probably come up at this point is why do we attack one carbon one time and one carbon the other time? That's a great question, and that's going to be the question that we're going to answer in the next video.